Welcome. Today we look at continuity. Let me first give you the definition. A function is continuous at some point x naught if the limit x goes to x naught, f of x exists, and independent of how we approach x naught. So it's a regularity condition at that point. There's no surprise at that point, and f is continuous on an interval if f is continuous everywhere. So this means informally that we can draw the function and we have not to lift our pen or our chalk when we draw it. So let me just draw you a continuous function. So this is a function, you can draw it, you can have corners like that, but this is a continuous function. If you take some point x naught here, and if x is close to x naught, right, if x is close to x naught, when x approaches x naught, then also f of x has to approach f of x naught. So this is a regularity condition. There should be no surprises when we approach this point x naught. It's easier to say what is not continuous, and I will just in the second part tell you about the enemies of continuity. There are three mechanisms which prevent a function of being continuous. So the first mechanism is a jump. It's called a jump discontinuity. And if you look at this graph here, and something like that, maybe the function value at that point is defined here. If you look at this function, then at that point here, x naught, the function is not continuous. And the reason is that if x goes to x naught, right? If x goes to x naught, we can be arbitrarily close to x naught. We have a different value, substantially different value than here. So the limit here is this value, while if you come from the other side, we get a different value. So these are called jump discontinuities, and they are quite frequent, especially in number theory, in signal processing, in neural networks, switches. There are many places where discontinuities like that appear. The second mechanisms we have already seen is the pole, or infinity, when we go to infinity, and the prototype example is the 1 over x. So we have in this case at x naught, so in this case x naught is equal to 0. In this case this really goes to infinity here. So this is infinities. So this is 1 over x, the 1 over x example. But there is another type of discontinuity which one often forgets about, and these are oscillations. So let me just take, this is type A, type B, this is not official, but type C, we have oscillations when we have a function which just gets crazy at the point. An example is sinus 1 over x. That's the prototype example. So if you look at this function, if you draw it with a computer, you will see it kind of approaches 0 and starts oscillating more and more and more. So this function is always between -1 and 1, but we have values like if you see here, when 1 over x is a multiple of pi, we get 0. So these are multiples of pi. And then pi half plus a multiple of pi gives you one values. So there are specific points here, arbitrarily close by, where the function value is equal to 1, I can just write you down, it's just 1 over pi half plus pi k. So if we take k equal to 0, then it's 1 over pi half. And if we take k equal to 1000, then we get, you know, something very close, 1000, about 1000 close to the origin. But still, if you take that and you evaluate sinus of 1 over that, you get actually 2 pi. You get equal to 1, and then we have here 1 over minus pi half plus 2 pi k. In this case, we have value minus 1. So here the f of x, if x is this, then f of x is equal to minus 1. If x is that, then we have f of x is equal to 1. And that's the function f of x. So this is an oscillatory discontinuity, and the graph is called the devil curve here because it just gets crazy around here. But that picture of the, you know, you can draw things without having to lift your pen is actually very, very good. In this case, if I draw this, I have to lift my pen and go up here and start drawing. Here, if I go here, I would have to go to infinity. In this case, what we have is, I'm just drawing it, I would have to go up and down infinitely often until I reach the point x0. So at that point, it's even not defined here. But we could say, for example, that at 0 we take the value 0. That would make it defined everywhere. The function is defined everywhere, but it's not continuous because we arbitrarily close find values where the function differs from the function value here. And I cannot save this by choosing any other point here. So this is very important. It's easier to say what is not continuous than what is continuous. Okay, let's look at some examples. In class, we look at this a little bit slower in more details. In this case, x squared, 1 over x squared minus 1. That's an example where we divide by 0 if x is equal to 1 or minus 1. So if I draw this function, so it has something like that. It actually goes to minus infinity here. And then at 0, it's minus 1. So it's this function here. So this is f of x. So in this case, there are vertical asymptotes here, poles here. So this is not continuous. Just make that. So this is not continuous. The second example, and we look at the second example, b. What happens here? We have no problem. We never divide by 0. So x squared plus 1 is continuous. 1 over x squared plus 1 is continuous because we never divide by 0. And indeed, that's an important function. It's called the Maria of Agnesi function. And we just draw that. It looks somehow like that. It looks like the Gauss, the bell curve. So this is 1 over. This is part b, and this is really continuous. Continuous everywhere. We have seen the graph of the log of the absolute value, right? So the function has roots at 1 and minus 1, but so it's everywhere continuous except at 0. So this is not continuous here, and it fails at the logarithmic singularity at 0 here. The next example, 1 over log x, that's an interesting case. Not sure whether I can draw that. But what happens is there are different problems here. So there are problems at x equal to 0, because then we have infinity here. There's also a problem at x equal to 1, right? Because then we divide, the whole thing is equal to 0. And this is actually not savable. We can, at x equal to 1 or minus 1, we really have a problem here. So this function actually goes to 0, and when x is bigger than 1, so if x goes to 1, so this goes to infinity here. There's no way we can save this. But actually what happens here at x equal to, so it comes from the other side somehow like that. I don't know whether I draw this right here, but at x equal to 0, this is actually continuous. Because when x goes to 0, this whole thing goes to infinity, and 1 over infinity goes to 0. So there is a definite value. It's not nice, not not smooth, but it works. It's just that at these points it fails. So this is not continuous. Here I have a sinus x over e to the x. So any function, basic function, sine, cosine, e to the x, polynomials, they are all continuous. We can also divide by e to the x because e to the x is never 0. So this is perfectly fine. This is actually sinus x times e to the minus x. Perfectly fine. This is a continuous function. I don't know how to draw that here. So this is kind of something, if you want to draw this. This goes at when x goes to infinity, this goes to 0. So it's something which oscillates somehow like that. And then at x equal to 0, so we get something like that. And then when x goes to negative infinity, then we grow. So this is a function which becomes larger and larger and larger here. But it's fine. It's perfectly fine everywhere. So this function is continuous. What about this function? So in this case, what we have in D, so this is, this is E, A, B, C, D. This is E. This is F. If you look at the function f, x squared is no problem, that's continuous. The tangent x is a problem. So if you look at that, so it's x squared, and then we have the tangent x, and the tangent x is this function here. So this has a problem at x equal to pi half and minus pi half. So that's why it's important to know these basic functions well. And so what happens is when we add them, we get still a problem here at this point. So we get a finite value here, pi half square for this, but here we get something which goes to infinity. In general, if you have something which is continuous and something which is not continuous at some point, we get something not continuous at that point. Let's look at G. These are examples we have looked at last time when we looked at limits. This is a function which is not defined at x equal to 1. So the function is, so let's just also say we take this and take 0, take f is equal to 2 at x equal to 1. And x is equal to 1, then we can still assign a value. So in this case, we still say this function is continuous. So even so, it is a priori not defined at x equal to 1. We have seen at this, looked at this function, right? It had a priori, it was not defined here. But usually, if we can continue something through the point, then we just consider this as a continuous function. So we just, if we assign here the value x equal to 2, at x equal to 1, we assign the value 2, this becomes really a continuous function. So it is continuous after a fix. And this function also, this function is a nice function, it's a sinc function, and sinc function, and the sinc function is defined everywhere we have seen. Function is a very nice function, and so it kind of oscillates, kind of goes to 0. So it was not defined here originally at x equal to 0, but we can fix that at x equal to 0. So we consider this a continuous function. So that's the modern point of view. In calculus books, usually you would say this is kind of not continuous, but at the modern point of view, any mathematician considers this a continuous function because it's you can extend the value to x equal to 0 where it is not defined. Also here, you can extend it to the point x equal to 1. You can just assign it a value to make it a continuous function.